Okay, all right. Well, good morning, and I hope you guys are doing well. I have posted to the modules. Let's see. I think these are visible to you. Midterm two topics and today's lecture notes. So those are there. Let's talk about midterm two. And you can tell me, I have not been on campus since they've kind of, you know, pushed us online. So I have no idea if this is completely kind of naive of me to think that we can have an in-person exam on Monday. Um, maybe campus will be open, maybe it won't be open. Um, as of now, I'm going to hope that campus will be open on Monday. And if it is, then we'll do our midterm then, okay? On Monday, May 13th. Um and it will be an in-person exam. If um but I've got some contingency plans, okay? Um if campus is closed on Monday, then I will delay the midterm until Wednesday. Okay. The only unfortunate thing about doing the exam on Wednesday is that well, I like to try to get the exams graded right away, but I'm going to be traveling um, on Wednesday, and so because because of the travel, it'll take a while to get things graded. Okay. But if yeah, so if campus is closed on Monday, then we'll postpone the midterm until Wednesday. Um, and I'll just deliver a lecture on Monday instead. If campus remains closed on Wednesday as well, so if it's closed Monday and Wednesday, then I will just cancel the entirely. Okay. Um, I don't want to delay it any further because I have travel plans and so I'll be gone on Friday and Monday, and then it'll like get pushed until eighth week Wednesday, and it just kind of throws everything off. I also don't want to do an online exam. And um so yeah, if campus is closed both Monday and Wednesday, I'll just cancel the exam in its entirety. Um and if that happens, then I will use a reweighted grading scheme. Okay. So right now, the way the syllabus has it declared is that right now it's midterm one and two are 15% each, and the final exam is 20%. If midterm two gets canceled, then as far as the exams go, I'll keep midterm one at 15%, and I would set midterm two. I'll reduce that to like 7.5%, half of its weight, and I'll just give everybody 100% for that canceled exam, the 7.5%. And then I'll bump up the final exam to 27.5%. Okay. And then what I would do is then I would kind of take some of the planned content from the midterm exam and put that on the final exam. And then, but I'll also just kind of adjust the final exam to make sure it's, an appropriate length. I'm not going to just take all of the midterm and throw it onto the final, and you'll have this, super long final exam or something like that. It'll just be like I'll take some of the midterm stuff and put it on the final. Okay. Um, I hope it doesn't come to this. I hope, plan A is campus is open and we do the exam on Monday, and things go okay. But yeah, I don't know what the status is, and uh, yeah, so that's where things stand. So, but assuming we do have the exam in person, then it will be a pen and paper exam, and um, we will have one sheet of notes. letter size 8.5 by 11 with and, writing on the front and back. And then again, I don't know if I need to add this, but put your name on the note sheet, and I will collect the note sheet with the exam. Okay, I'll also be sending out a seating chart. Same kind of idea that worked for midterm 1 as well. Okay, anybody have any questions regarding I guess this midterm stuff, or like what the plan is? Does this make sense? Or I don't know, what is your sense regarding campus reopening? I imagine you guys being closer to campus, you have a better idea of what's happening. I only get little like once a day updates from what's it called? Bruin Alert. So I don't know. It's like a weird police state. Oh, geez. Okay, well, that's not great. Yeah, it's always uh it is always a little disturbing when there's like an inordinate amount of law enforcement presence on campus. It just feels, yeah, it feels like uh-oh. Okay. All right. Well, we'll see if campus opens up for Monday, we'll do that, and then if not, this is our plan. Okay. All right. Well, so again, assuming we do have a midterm either on Monday or Wednesday in person, this is what your exam would look like. We will so I've got kind of a list of topics here, and out of this list of 6, I would probably pick 4, maybe 5, 4 or 5 of these things. So this is kind of what we're looking at. So one is calculate a numeric gradient. So you did this in the homework, and I would give you a very simple neural network with one hidden layer. So kind of like in our class we had 2 nodes in the input layer, 3 nodes in the hidden layer, 1 node in the output layer. It'll be something kind of like that, a very simple network. And there will be a very kind of simple identity function, simple activation function. So I will not use the sigmoid function just because as useful as that activation function is, it just makes the calculations way harder, and I don't think it actually tests your ability. So the activation function will be something simple like the identity function, meaning you don't transform the value at all, or the ReLU rectified linear unit, which is basically the identity function if x is positive, and then it just flattens it to 0 if x is negative. And then your loss function, you'll have a loss function to measure maybe the mean squared error, maybe the sum of squared errors. I will specify. There will be a tiny little input set of data, so maybe like 2 observations in your input set, and I will provide initial weights, and then you will calculate the gradient numerically, okay, by kind of not by doing back propagation, but instead by kind of perturbing. You add a tiny little epsilon, and then you have it kind of go through, and you'll see how much it changes the loss function. And then you get an estimate of the gradient by measuring how much the loss function changed and versus how much of an epsilon you added. Okay. Another possibility is to do the analytic gradient. Very kind of simple neural network again. And in this case, the activation function will just be the identity, okay? And then you'll have either mean squared error or sum of squared errors for your loss function. Again, another tiny input set of data, and I'll provide the initial set of weight and bias matrices if we include bias matrices. And then you'll calculate kind of the gradient of one of the matrices analytically. So you'll find like, what's DJ DW1 or whatever like that, okay? I would recommend for your page of notes to have the formula for the, given that it's a neural network with one hidden layer, you can, as far as your notes go, you can have the analytic gradient written out. So you don't have to kind of go through all of back propagation during the exam. But be ready for either the gradient with respect to W1 or the gradient with respect to W2 or the gradient with respect to B1 or B2, either with or without the matrix, without the bias terms. Okay. All right. Another possible problem is maximum likelihood estimation. And I will provide some kind of univariate probability distribution. So some kind of either PDF or the PMF if it's discrete. So I will provide, think of something like the exponential distribution or the Poisson distribution or the normal distribution, some kind of univariate distribution. And one of the parameters will be unknown and you have to estimate it with the data. So for example, if the univariate distribution were the normal distribution, maybe I would say the mean is unknown, but the normal distribution has two parameters. So we'll say, just assume the standard deviation is this and hold the and hold that constant. And the mean is unknown in this case. Okay. Or if you have the binomial distribution, then that has two parameters, n and p, and we'll say n is constant and p is unknown, or something. Or if it's like the exponential distribution, then there's just one unknown parameter. So that should be fine. Okay. And then I would provide like a sequence of observations. And then based on the observations, you'll figure out the maximum likelihood estimate, okay? And then and then from there, you'll also calculate the Fisher information. And again, Fisher information can be found by doing the negative expected value of the second derivative of the log likelihood with respect to the parameter, right? So you take the log likelihood and you take the second derivative with respect to the parameter, and then you'll take the negative expected value of that. So calculate the Fisher information for this thing. Okay. And then the Bayes classifier. So I will cover the Bayes classifier in today's lecture. And so here is some problems that could involve the Bayes classifier. You could have a Bernoulli or binomial example for the Bayes classifier, which is, we have an example of that in today's lecture. Basically, you'll have a mixture of observations, and based on what you see, you have to try to guess, which class the kind of the probability of the class for the different test case, right? And then you'll also have a Bayes classifier with the normal distribution. I have something very similar to this in today's lecture notes as well. It's just the one in today's lecture notes, you have a multivariate normal distribution, and in the if I were to have this on the exam, then it would be a univariate normal distribution, okay? So it would just be simpler case. You would need the PDF, and you would calculate the PDF of your observations accordingly, and based on your probabilities, you'll do some kind of classification calculation. Okay, and then some conceptual questions. Okay, and then the conceptual questions would span from lecture 3.2, where we started neural networks, up to lecture 6.3, which covers the naive Bayes classifier. So Friday's lecture is going to be on, so today's lecture is on the Bayes classifier, and Friday's lecture would be on the naive Bayes classifier. Okay, so that is the list of topics for midterm 2. Again, assuming we have the midterm on Monday or Wednesday in person. And then, and I'm going to just keep in mind that there's a possibility that things change, and I just have to cancel the exam in its entirety. Which, I don't know. I don't know how we feel about this. I was trying to think like if I were a student, what would feel fair to me? But also like something that I, as the teacher, am willing to do. And this is what I came up with. And if you feel like, midterm 2 being canceled and this is unfair or something, you let me know. But I think this is what I felt like. I think if I were a student, I'd feel like this would be fair. Midterm 2 gets reduced, the final exam gets weighted heavier, but then everybody gets 100% on the midterm 2. And I felt like this is kind of some compromise solution there. Okay. All right, let's get into today's lecture. Okay, yes, so some students have take exams with CAE. I guess I will, well, I think I don't know what happens, but I imagine CAE will be aware that, like, oh, you know what? Campus is closed. And then so I guess I'll message CAE and just say, like, if campus is closed, then we'll I'll tell them either to reschedule the exam or cancel the exam as well. So I'll message them. But yeah, it is we just have to be flexible. So that's just, I mean, that's all of life really, is being a little bit, trying to be a little bit flexible. So yeah, okay. Important. All right, so let's talk about the Bayes classifier. All right, so now we are moving into classification methods, okay? And the idea with classification is that you have these observations, and each observation is associated with some kind of class label, some kind of category. We're going to say there are C classes, 1, 2, 3, 4, 5, up to C. Now, and then the goal is to predict what is the label, okay? Which class does some new observation, X new, belong to, okay? Now, one thing to keep in mind is that even though these class labels are integers, like 1, 2, 3, 4, 5, we treat them as categories. Like class label 2 is not twice as big as class label 1, and then you want to predict only something like class label 2 or class label 3. You can't, there's no meaning behind trying to predicting a value like 2.5. Okay. You can only predict one class there. Okay. The way the Bayes classifier works is it uses Bayes' rule, and and you get a probability. So the Bayes classifier is a probabilistic classifier, and it will return basically a vector of probabilities that would add up to 1 for each of the different classes. So let's say you have 3 classes, A, B, and C. Just an example prediction would be something like class A with probability 19%, class B with probability 80%, and class C with probability 1%. Okay, right? So you have three probabilities, they add up to 100%, and you get kind of a probability for each of those classes. Okay, another example of a probabilistic classifier would be something like logistic regression, but that one is just 2 classes, and it's going to predict, the probability that it belongs to, one of those classes. There's another kind of classifier, and that is the hard classifier. And that one is just going to say, this is class B, or it's class A or something. Examples of hard classifiers would be, or non-probabilistic classifiers would be things like k-nearest neighbors and support vector machines, and we'll talk about both of those things. Now, one thing I want to kind of distinguish is that even though this is the Bayes classifier, this is not considered Bayesian statistics. Okay, Bayesian statistics is kind of like an entirely different what do you call it, philosophy regarding probabilities, and that I covered that in Stats 102C. So this is the Bayes classifier, but it is not Bayesian statistics. Okay, well, remember this is Bayes' rule, okay, or Bayes' theorem or whatever. We say the probability of A given B can be found by taking the probability of, A intersection B in the numerator, which is can be calculated by doing probability of B given A times the probability of A, and then you divide by the probability of B, okay? And this denominator, probability of B, you can kind of decompose it into the probability of B given A sub n times the probability of A sub n, and you sum it across all of the different possible values of A. So, so you can decompose the bottom into basically, B given A times the probability of A, but you have to calculate it for all of the different, whatever A can be. So A can be like 3 different classes, and you calculate it for all of those things. And so it's basically the numerator, but you calculate the numerator across all of the different possible values of A, and then you add them all up. So, so this is basically what we want to do. We want to take Bayes' rule, and we want to calculate, okay, what is the probability that a new observation belongs to class C, given the values, the X values in that observation, right? Along with given all of the training values and all of the training labels, okay? So we want to know what's the probability that the class label of T is equal to, C, whatever it is, given the X values, all of the training data and training labels. All right. It's a probability, so it follows some probability rules. So these are just kind of like, did I mess up? Checks that you can do. So your probability needs to be a value between 0 and 1. If it's not, you messed up somewhere. Okay. And then if you calculate the probability for all of the different possible classes, all of those probabilities have to add up to 1, okay? So again, if you have 3 classes, A, B, and C, your 3 probabilities have to add up to 1, like 19%, 80%, and 1%. That would add up to 1, and then that would be a potentially valid classification. So if we stick, if we say, okay, well, here's Bayes' rule, and let's do that for, what's the probability of our new observation having class label C. This is given, all of the kind of information provided. We call this thing probability of T new equals C, given kind of your X new observation. That's the probability we want, and we call that thing the posterior. Okay. The other side, we have the likelihood, which is what's the likelihood of getting the X values, the probability of the X values, if we assumed the observation belonged to class C. We'll multiply it by the prior probabilities, which is just before we even look at the values in X new, what is the probability that an observation belongs to class C to begin with? That's the prior probability. And then we divide by the marginal probability, which is what is the probability of even getting these X new values, whatever the values I had in my observation X, regardless of class labels. What is that probability? Okay, let me give you your first view quiz answer, and that is the letter D. D as in dog is your first view quiz answer. Okay, we can apply the law of total probability, and we can decompose this denominator into basically the numerator, and we'll sum it across all of the possible cases. Okay, so if I wanted to know, hey, what's the probability of X new? Basically, I could calculate, okay, what's the probability of X new for class A? What's the probability of X new for class B? And what's the probability of X new for class C, right? So if your X values are, say, I don't know, let's say your X value is 7, you can say, hey, what's the probability of getting the number 7 if it was class A? What's the probability of getting the number 7 if it was class B? What's the probability of getting the number 7 if it's class C? You calculate the probability across that, and then you sum that across all of the possible classes, and that will be the value of the denominator, the marginal probability on the bottom. Okay, so this is like a whole bunch of formula stuff. I think it will, maybe, I hope it will make more sense if I just do an example. Okay, so this is a very silly example, but hopefully it will get the job done as far as explaining how something works. Okay, so let's say you buy like a little pouch and it's got marbles in it. So I mean, this pouch is probably too small, but you buy some pouches. They've got marbles in each of these pouches, and you buy, I don't know, 25 of these pouches. Okay, and the pouches, I don't know, you look at the serial numbers on these pouches or whatever, and you realize like, oh, you know what? They have 3 different factories. Okay. 3 different factories. And these factories all produce, pouches of marbles, and I don't know, these the pouches contain, red marbles and blue marbles, but it looks like the different factories have different kind of filling proportions as well. Okay. And kind of you have these 25 different pouches. 24 of them are labeled with their factory. So 12 of them came from factory A, 6 came from factory B, 6 came from factory C, and the last pouch isn't labeled, and we got to try to guess which factory did it come from. Okay, and we're going to assume the bags are filled with some kind of Bernoulli process here. All right, so this is silly, right? You got these 25 bags, 24 of them have labels. Some are A and some are B and some are C, and then we have one case not labeled. We got to try to figure out and guess, hey, is this A, B, or C? Okay, and so you go and you look at all of your data, and you say, well, you know what? It sure looks like, all of these pouches that came from factory A, most of the 60% of the marbles are red and 40% are blue, right? So you look at the pouch and you go, now it's not that every single pouch is exactly 60% red and 40% blue, but overall, if you look at all the pouches coming from factory A, you've got kind of, one bag might have been 65% red, another bag might have been 55% red, another bag was 60% red, something like that. And overall, when you look at the average of all of the pouches, or if you just kind of pool all of their marbles together, then kind of it looks like factory A is 60% red. Okay. And then you do the same thing with factory B, and it's like 50% red, 50% blue. And then for factory C, it's like 40% red and 60% blue. Okay. So we don't know exactly what the fill proportions are at each factory, but it does seem like there is a little bit of difference between these three different factories. And right now these represent, 60% red, 50% red, 40% red, kind of it represents our best guesses for the proportions of each factory based on the data we've observed so far. And there's nothing in our data that makes it feel like it's not a Bernoulli or binomial process, being like whether a marble in the pouch ends up being red or blue is just kind of equal probability no matter what. Okay. And yeah, so one pouch from factory A maybe is 70% red, 14 red out of 20 marbles. Maybe another pouch from factory A is 11 red out of 20 marbles, 55% red. And overall, the proportion from factory A that's red is 60%. Okay. All right. Does this kind of make sense so far? Just like the setup here. So what we are going to do now is we say, okay, well, let's look at this last bag that's not labeled. And we open it up. Okay. We dump out the marbles. In that bag, there are 20 marbles, 10 are red, which means half of the marbles in the bag are red. Okay, and now we have to say, all right, let's try to guess which factory produced this bag. Okay, so what we can do is we can calculate the likelihood. We can say, what is the likelihood of getting my data? My data is 10 red marbles out of 20 marbles. So 10 red out of 20, if I assumed it came from factory A. So if I assume it came from factory A, my probability calculation would be 20 choose 10. And factory A, remember, is 60% red. So I would do 0.6 to the 10 times 0.4 to the 10. And you do that calculation, you get 0.117. What is the likelihood that it came from factory B? Factory B is, we're assuming to be 50% red. So my calculation would be 20 choose 10, 0.5 to the 10, 0.5 to the 10. And that calculation comes out to be 0.176. And then I do the same thing for factory C. Factory C is 40% red. So I say, okay, what's the probability I get 10 red marbles if it came from factory C? Factory C, we do 20 choose 10, 0.4 to the 10, 0.6 to the 10, and well, it's like symmetric. So we get a likelihood of 0.117. The probability there is a little bit lower. And so looking at the likelihoods, we see, oh, you know what? Factory B has the highest likelihood. Okay, which makes sense, right? Because my bag of marbles that I'm looking at is 50% red, and that lines up most closely with factory B, where factory B, 50% of the marbles are red. But we say, hey, could it have come from factory A? Yeah, it could have come from factory A because factory A fills bags 60% red. And so, if factory A produces 60% red and it filled up a bag with 20 marbles, is it possible that you get a bag of marbles with only 10 red? Sure, that could happen. What's the likelihood of that happening? 0.117. Could it have come from factory C? The answer there is also yes, 0.117. Okay, so these are the likelihoods. this is the likelihood of getting my data 10 red out of 20 marbles. So this is my observed data. So I'm saying, so that's this. What is the probability of getting our data if we assumed or calculated it for class A, for class B, and class C? Okay, that's the likelihood. Okay, I hope that's okay. And meanwhile, we have to balance the likelihood. So we don't want to just say, okay, we did our likelihood, and therefore we're going to assume it comes from factory B. Okay. Now we have to balance that with what we would call our prior probabilities. And we say, before I even opened any of the bags, okay, before I opened my test case, when I looked at my training data and stuff, if before I looked at it, if I just said, hey, try to guess whether it came from factory A, factory B, or factory C, don't look in the bag. Prior to looking inside the bag, try to guess whether it came from factory A, factory B, or factory C. We would say, well, you know what? It looks like factory A produces most of the, or half of the bags, right? 12 out of my 24 bags came from factory A, whereas only 6 came from factory B and only 6 came from factory C. So if I had to guess, um, my prior probability before I even look at the X, I would say it comes from factory A with probability 0.5. It comes from factory B with probability 0.25, and it comes from factory C with probability 0.25. Okay, so these are my prior probabilities, and we do that. Okay, so that's these are my prior probabilities. And so what we need to do is we're going to combine the likelihood, which is the binomial probabilities, and we will multiply it by these prior probabilities, because that's basically looking at our formula. That's what the numerator is. Okay, the numerator is the likelihood. That's kind of the result of the binomial probability times the prior probability. What's the probability that it belonged to a certain class before I even looked at the data? Okay, so we're going to calculate that numerator, and that's just taking the product. We just do the likelihood times 0.5. Here's the likelihood 0.176 times 0.25. And then the likelihood for class C times 0.25. Okay, and we get these numbers 0.058, 0.044, and 0.029. Right? And okay, and this is basically my answer. I just have to scale these up, because if I add these up, they don't add up to 1. So I just need to scale these up so that these 3 probabilities, or these 3 numbers, would add up to 1. Okay, and so the way I'm going to do that is I'm going to divide by the marginal probability. So I take these numbers 0.058, 0.044, 0.029, and then that adds up to 0.132, 0.1319. And we will scale everything up by just taking these numbers and dividing by 0.1319. Okay, and that's what the denominator is. The denominator is the numerator summed up across all of your possible classes. So we had class A, class B, class C. We're going to add the denominator across all possible classes. And that will be, hey, what's the probability of getting 10 red out of 20 marbles regardless of class? Okay, and we'd say, oh, you could get 10 red out of 20 marbles if it came from factory A. You can get 10 red out of 20 marbles for factory, and it comes from factory B. What's the probability of getting 10 red out of 20 marbles if it comes from factory C? You add those up and you get 0.1319. So the final probability is, all right, what is the probability that it belongs to class A, given that we observed 20 red marbles, or sorry, 10 red marbles out of 20 marbles in the bag, is equal to the likelihood times the prior divided by the marginal. And so that numerator is 0.0585 divided by the marginal 0.1319, and we get 0.444. Okay, 0.444. What is the probability for class B? You do the same thing. The likelihood, that's the binomial probability times the marginal, or prior probability, which was, 6 out of the 24 bags came from factory B, divided by the marginal, the sum of the numerator across all possible places, we'll get 0.334. What about class C? You get 0.222. And those are your answers. So our three probabilities are 0.444, 0.334, and 0.222. Okay. And this reflects kind of the combination of our prior data versus our the prior probabilities along with the data we've observed. So in our test case, in our bag of 20 marbles, we got 10 red. It's 50% red, okay? And if we were to base our classification only on that information, we would have picked factory B, right? Because in our training data, factory B was 50% red, factory A was 60% red, factory C was 40% red. My data comes out to be 50% red, so factory B has the highest likelihood, okay? But we also take into account the prior probabilities. The prior probabilities said that half the bags came from factory A, where only a quarter of the bags came from factory B, and a quarter of the bags came from factory C, okay? And so when we combine that, the result ends up kind of readjusting that. So if I didn't know the data, what is the probability it came from class A? If I was just basing it off of the prior proportions, I would have said, well, half the bags came from factory A, so I'm going to assume this one has a probability of 1/2 of coming from factory A. However, once I factor in the data where it was actually only 50% red and not 60% red, that probability goes from 0.5 and it drops down a little bit, not dramatically, but it drops down to say 0.444. Here, before I looked at the data, what was the probability it came from class B? That was 0.25. After seeing that my data was 50% red, which aligns with class B, my probability bumps up a little bit to 0.334, okay? And then prior to looking at the data, what was the probability it came from class C? It was 0.25. And then after looking at the data, and my data do not align perfectly with class C, where it was only, because class C is 40% red and my data came in 50% red, seeing that they didn't align there, I adjust it down from 0.25 down to 0.222, okay? And that's what we have. Now, there are a few major assumptions that went into this classification model, and that was we assumed our maximum likelihood estimate probabilities, where we opened up all of the bag and we said, hey, I think factory A is 60% red, that's a strong assumption, right? We looked at our data and we said, I think 60% of the bags, factory A has a fill proportion of 60%. So, I mean, that assumption could be wrong. And then the other thing was, out of the 24 bags, 12 of them came from factory A. So now I'm assuming factory A produces half of my bags, okay? Also, a strong assumption that could be wrong, okay? Now, if you were like an inside worker and you know something about the factories and you go, oh, you know what? Factory A, B, and C, they all have the same production. They all produce the same amount of bags. I don't know what happened with your batch of bags. If you've got 25 bags, I would have thought, a third of them come from factory A and a third come from factory B and a third come from factory C or something like that. So somebody might have some inside information to tell you, oh, you know what? It's not 50% A, it's something, more balanced. And then you change your prior probabilities to say like 1/3 for each of the different classes, okay? So what would affect kind of your prior probabilities. What if we have a different test case, okay? A different test case, let's say you open up your last bag and there's only 6 red marbles out of 20, okay? 6 red marbles, so it's only 30% red, okay? We're still gonna say like half the bags came from A and a quarter came from B and a quarter came from C, but now we'll calculate the likelihoods and we'll multiply it by the prior. So we can say, hey, what is the likelihood that factory A produces a bag where there's only 6 red marbles? Okay, well, that's going to be 22 6, 0.6 to the 6, 0.4 to the 14, okay? And then we do the same for factory B and factory C. Factory C is going to have the highest likelihood because it's 22 6 and then 0.4 to the 6 and 0.6 to the 14, okay? So, and then we're going to multiply those likelihoods times the prior probabilities of 0.25, 0.25, and 0.25. And I don't know if you can see, it's a little bit hard to read, but that numerator for class A is going to be 0.0024. The numerator for class B is 0.0092. And then for class C, it's 0.0311. So class C now has the highest kind of likelihood prior combination because this bag is only 30% red. So now it's like, what's the probability it came from class A? Class A has a 60% fill proportion of red marbles. What's the likelihood it's going to produce a bag where only 30% are red? Now we go, oh yeah, you know, it's pretty unlikely that it's coming from class A, okay? But class C has a fill proportion of 40% red. So this one's the one that's most likely to produce a bag where it's only 30% red. So it ends up having, you know, kind of the highest probability. So these are the numerators. You added the numerators across all of the possible values. You get 0.042. And then when you do your posterior probabilities, you get something around 0.0567. So now the probability that it came from class A is around less than 6%. The probability it comes from class B is maybe around 22%. And the probability that it comes from class C is around 72, 73%. So class C now has the highest probabilities. Okay. So yeah, this kind of takes into account basically what we see in the data. How likely is it for a different factory to produce a bag where only 30% of them are red? And so it's very unlikely to come from factory A and not super unlikely to come from factory C. And so when you take that into account, these are the probabilities you get. Okay, ooh, we are out of time. So let me give you your last 2 view quiz answers, which are the letters B and A. So the second answer is B, third answer is A. That will be our last 2 view quiz answers. And I guess I'll have to continue this and we'll talk about the Bayes classifier for a mixture of, I guess, multivariate normal distributions. We covered the multivariate normal distribution a little bit earlier. Was that Monday's lecture? I think it was Monday's lecture. And so, you know, this is the PDF for that. And then using that, we will go through and we'll do a Bayes classifier there. Okay, so I guess we'll have to continue this on Friday to cover the Bayes classifier. I'll also post homework 4 up, although regarding homework 4, you know, we just started covering the Bayes classifier, and you know, homework 4 is basically all of these different classification methods and algorithms, and so you can start to take a look, but don't be discouraged if you can't do any of it right now, because we've only covered a little bit so far. Okay, we'll end here for now. We'll see you guys on Friday, and we'll continue where we leave off and talk about the normal distribution Bayes classifier there. All right. Have a great rest of your day.